This video contains explanations for the practice problems that go with the thermo unit. I've written the answers out and circled each of the questions, so if you just need to fast forward to a question, just fast forward to that question's number for the slide, and that's where you'll find the answers written out. Real quick, question number 1. The thermodynamic quality that expresses the degree of disorder. So if we're talking about disorder, that means we are talking about entropy. Definition. Question number 2 asks us to calculate the value of delta H for the reaction if we are just using 2 moles of sodium hydroxide, and the reaction is written for 4 moles of sodium hydroxide. So if we know the enthalpy of this reaction, we know that it's exothermic, it would give off 126 kilojoules. Then if we use 2 moles, that's only going to be half. So half of 126 is going to be 63. Number 3. Stoichiometry problem. We are given that we have 16 grams of C6H6, and we know the enthalpy of this reaction. It's given in the question. So we are just going to have to use stoichiometry to figure out the amount of heat produced from 16 grams. So first, grams to moles, and then using the molar ratio for every 2 moles of C6H6, we get 6,535 kilojoules. We just calculate, plug in the numbers, watch your mental math. 16 divided by 78 ends up being 0.2, and then we have negative 6,535 divided by 2. So 0.2 divided by 2 is 0.1, and 0.1 times 6,535 gives you about 650, and we can go and find the answer being D. Question number 4, another stoichiometry problem. They give us that you have 13.7 grams of barium, and they want to know how many kilojoules of heat are released. Again, you're going to have to do some mental math. Notice that they use 13.7, and the molar mass of barium is 137 grams. So that ends up giving you 0.1, and so we have 1,107 divided by 2, and so that gives you a simplified answer of 110.7 divided by 2, which would give you 54. Question number 5, we're going to transition to some calorimetry. They give us the specific heat of lead. They ask how much heat is required to raise 10 grams of lead, 20 degrees Celsius. So we know the mass, we know the specific heat, and we know the delta T. And so watch easy math. 10 times 20 gives you 200. Times 0.13 would end up giving you 26. Another calorimetry problem. This one's going to take a little bit more time because it goes through all the calorimetry steps. And there's a couple of tricks in this question, so be aware of it. So they give us the delta H for the reaction. They tell us the enthalpy of the reaction. And they give us some information. We're dissolving sodium hydroxide into 250 grams of water, and the temperature increases from 23 to something. So they're going to ask us to find this delta T. So there's a couple of things we have to pay attention to. Why did I put a negative sign on the delta H? Well, they told us the temperature was going to increase, and that tells us that the dissolving is exothermic reaction. So we have to watch our signs here. So we know the delta H for 1 mole of sodium hydroxide. But we're not using 1 mole of sodium hydroxide. We are using 13.9 grams. So we're going to have to calculate how much heat was produced by 13.9 grams. So we know the enthalpy, we know the moles. That will give us our Q. Our Q is going to equal negative 15 kilojoules. We also know our Q expression. Q is equal to the mass times the specific heat times the delta T. So if we plugged in the mass and we plugged in the specific heat, and here's our delta T, that's going to allow us to find the final temperature. Watch out again, because the specific heat is in joules, but the enthalpy was in kilojoules. We're going to have to change that. So we have to change the 15 kilojoules to positive 15,000 kilojoules. Why is it positive? Because we're going from heat of reaction to heat of solution. The sign is going to change. And so we end up having 15,000 kilojoules is equal to our mass times our specific heat times our delta T. I rounded those to easier numbers to be able to do the math. So 15,000 is equal to 1,040 times our delta T. And so solve for that. We can find that our final temperature is somewhere around 38. So when we go to our choices, we can easily eliminate C. We can easily eliminate D because so we're left with A and B. Very, very close. And honestly, I think they wouldn't give you values that are this close. But how do we choose which? Well, remember we did a lot of rounding. We did a lot of rounding up on things. So when we were doing our calculations, rounding down on our things. So when we were doing our calculations, we went into the down direction. So that's going to mean that when we do our we do our real calculation, the temperature is going to be closer to 37 degrees Celsius. And if you type this into a calculator, you would get exactly 37 degrees Celsius. Number 7, we're given multiple steps and we're asked to get the enthalpy of the overall reaction. So what do we have to do for each of these steps? First step, we're going to have to multiply to fix the coefficients. Second step, we're also going to have to multiply to fix the coefficients. So then we just add up those enthalpies together and we get the overall enthalpy of the reaction. Number 8, sort of a stoichiometry problem, sort of a stepwise problem. They're telling us the enthalpy of the reaction is negative 186 kilojoules, or positive 186 kilojoules of heat would be produced. So they're asking what's the value of the enthalpy of formation of HCl. Well, keep this in mind. Negative 186 kilojoules is equal to 2 times the products, which is HCl, minus the reactants. Well, because both of our reactants are elements, the reactants are going to be 0. So now we just solve for HCl. So HCl is equal to 186 divided by 2, which gives you negative 93. Number 9, summation law. Just plugging and chugging. Plug in the values. Don't forget the coefficients. Make sure you do products minus reactants. Do some mental math. Round these things to whole numbers to make your math a little bit easier when you're doing mental math. But otherwise, that's a pretty straightforward problem. Again, summation equation. Don't forget your coefficients. Don't forget to do products minus reactants to get your enthalpies, and you end up with negative 140. Another summation equation for enthalpy, but this one's a little bit different because they're giving us the overall, and they're asking us to find one of the things in the reaction. They're asking us to find the hydrochloric acid here. So just plug it into your equation, put hydrochloric acid as an unknown. You can write X, you can write enthalpy of formation of hydrochloric, and then just solve for that. So when we do our algebra correctly and solve for things, we end up with the enthalpy of formation for hydrochloric acid is negative 184. Number 12, we're getting into bond energies. So remember, when we're calculating enthalpy using bond energies, it's bonds broken minus bonds formed. So look at what bonds are broken. We have the carbon triple bond is broken, 2 carbon hydrogen bonds are broken, and a hydrogen iodide bond is broken. On the form side, a carbon double bond is made, 3 carbon hydrogen bonds are formed, and a carbon iodide bond is formed. So one of the things that you can look at is the fact that we have some bonds that are broken and formed that are the same. So we really don't have to use all of this, because really the only thing that happened was 1 carbon hydrogen was formed. So let's just cancel this one out and change this to a 1. That's going to make your math a little bit easier. But if you have a calculator, break them all, make them all, no problems. But if you're having to do some mental math in your head, just calculate the broken ones and the formed ones. Number 13, broken minus formed, again, bond energies. And you can see when I worked this one out, I didn't break them all. I looked at what stayed intact and what was broken. So the broken ones, the carbon double bond, the hydrogen bromine bond, the carbon hydrogen bonds, they stayed intact. Formed, we formed a carbon single bond, 1 carbon hydrogen bond, and a carbon bromine bond. Plug in the values into your equation, and that's going to give you your overall enthalpy. Now we're moving into some entropy questions. They ask us to calculate delta S, and they give us the entropy values in the table. Well, it's a summation equation. Just plug everything into the summation equation, products minus reactants. Number 15, calculate the delta S. Plug things in from the table, products minus reactants, do some mental math. You get somewhere around negative 500, which means your answer is going to be your answer is going to be D. Number 16, again, use the table, summation equation, plug in your values. Round to make things easier, so you see I made that 400, and that's going to get me pretty close to the correct answer, which for number 16 is C. Back to calculating delta H's using the summation equation. Everything's in the table. This one should be a pretty quick one because your elements are 0 and 0. And sometimes you forget and you go look it up, and there they are right there in the table. 0, 0, 0 for your elements. Number 18, again, use the table, summation equation. Elements are 0, use mental math. That's going to allow you to get pretty close to the actual answer, and for 18, the answer is D. Calculating delta G using the summation equation. If you've got the delta G's, just use the summation. Makes your life easier. Can you go through calculating H and S and then get G? Sure, but that's going to require you to do 3 calculations versus if you have the delta G's, you can just do 1. You'll get the same results, but you might mess up some math if you're doing lots of math. So try to take the easiest route. If you're given delta G's, you use a summation equation to get the delta G values. Again, summation equation using delta G values. Check everything. Make sure you've got your delta G values correctly. Use mental math, round things to nice, easy whole numbers. It'll make your life easier. Calculating delta S using summation equations. Plug and chug. 22 is going to require you to use a calculator, only because you're going to have to be using logs, or natural logs and inverse natural logs. If you can do 22, then you've got this, because this takes care of everything you have to calculate in thermodynamics. So start with what they're giving you. They're asking you to find the equilibrium constant. I know we probably don't understand the equilibrium constant yet, but we can still calculate it. So when they say equilibrium constant, they're wanting us to find K. All right, and then they give us the information in the table below. They're giving us H's and S values. So the question is, how do we go from H's and S values to K's? So we can use all the delta G equations that are given to you on your equation sheet. We know delta G is equal to delta H minus T delta S. So if we have H's and S's and we know the T, which we do, they gave it to us, we are going to be able to find the delta G. The second equation that we can use, delta G is equal to negative RT ln of K. And here, if we know the delta G, and we're going to know R, that's a constant, and we're going to know the temperature, we can calculate the value of K. So this is going to connect you through these concepts, and it's a lot of math and a lot of understanding. And so if you know a little bit about the calculation, you'll be able to completely go through here. Watch your algebra, make sure you do your algebra correctly. So first, let's calculate delta H's. We have, the table has enthalpy of formations, so we're going to use the summation equation, calculate your delta H. Next, calculate your delta S's. Again, from the table, use the summation equation, delta S. Now we can calculate delta G. Here's the trick. S's are in joules, H's are in kilojoules, so we're going to have to change one. So I typically change my S's to kilojoules, so I changed my S to kilojoules, plugged in chug, and that gave me my delta G value. Now, once I have my delta G value, I can come and plug it into this delta G equals negative Ratlink equation. Again, units are a trick thing here because you got to watch your units. R is a constant. R is 8.314 joules per mole Kelvin. And so you're going to need to make sure your delta G is in joules, and that's going to allow you to, your units to cancel out. So let's start plugging things in. I've changed my delta G to joules per mole. And there's my R, and there's my T. Now keep in mind, all of this is an exponent. It's the exponent of the inverse natural log. So do that part of the calculation first. Do the delta G divided by negative RT. Don't lose your signs. And you get 56. And then we take the inverse natural log of 56, and that gives us a K of 2.57 times 10 to the 24. A lot of math there, but you went through a whole bunch of concepts: enthalpy calculations, entropy calculations, delta G calculations, and a K calculation. '23, they gave us the value of K. They asked us to calculate the delta G. Just plug it into negative rat link, RT ln of K, and you'll be able to calculate your delta G. Watch your units. When you calculate it using this equation, you get joules per mole, and you got to change it to kilojoules per mole. 24 is just like 22. We're going to have to work through all the equations. Calculate your delta H. There's the delta H value. Calculate your delta S. There's the delta S value. Plug it into delta G equals H minus T delta S. And watch your units, and you get negative 91. Plug that into the K expression, negative rat link, and you end up with a K value of 9.2 times 10 to the 15. '25, we're back to a calorimetry problem. They're asking us to find the specific heat. If we know how much heat is produced, and we know the mass, and we know the delta T, so we just plug into the Q equals MCAT equation and solve for the specific heat. '26, that's a stepwise problem. What are we going to have to do? To the first equation, we're going to have to flip the first equation. For the second equation, we're also going to have to flip it. And when we flip the equations, we flip the signs. So we end up with negative 180.7 plus positive 113 gives us negative 67.6. 27, another practice with the summation equation. Plug things in from the table into the summation equation. Round so that you guys have easier mental math, and then find the most appropriate answer. 28. Which of the following conditions will result in an increase in internal energy of the system? So how is the system going to have more energy? First, energy must come into the system. That means it's going to gain heat, meaning it's endothermic. And work must be done on it by the surroundings. So work is done on the system by the surroundings. Then we are adding energy, internal energy, in the form of heat and work. 29. A chemical reaction. A chemical reaction that absorbs heat from the surroundings is said to be, well, we're absorbing heat. That means we're taking heat in. It's said to be endothermic. And endothermic reactions have positive delta H's. Last question is number 30. You might need a calculator for this one. So they're giving us the K. They want us to find the value of delta G. This is a negative rattling question. So plugging things into the equation. Your R, your T, the natural log of your K. Watch your units, because when you finish this calculation, you're in joules per mole, and the question wants you to give an answer in kilojoules per mole.